So, as I just promised, let's talk about it. Control system architecture. So, we would like to see that how actually we are going to do as a whole picture. Because as I promised, we do have different chapters we would like to cover, 8, 9, 10, and 11. So let's see from the big picture. So as we have in the chapter number 8, we would like to talk about the root locus analysis. Why we do have that? Because as I just mentioned, in the root locus analysis, or we just saw in the book itself, we have to predict the transient response and pole migration. It means that at this point, we have to find the poles and we have to find the zeros. And we would like to see that by changing the k or gain, because as we know, changing the gain means that the places of some kind of the poles would change also, and poles and not zeros obviously, just the poles itself. So based on that, we would like to see how actually everything would change. Is it going to get completely unstable? Is it going to stable? And by using some kind of compensators, we have to make sure that we are in an ideal condition. For chapter number 9, we are talking about designing with root locus. So far, we understood what happened with the poles and some kind of zeros, and I just mentioned we need the compensators. By compensators lead, and by using those compensators, we are trying to move whatever that we do have on the right side of the S-plane. By the way, S-plane means that there's a plane that we do have the sigma as a real one, and we do have the j omega as the imaginary part that would show the places of poles and zeros. So by using compensators, we would like to move everything that is happening on the right side to the left side, because we know if we are moving or if we are working on the right side of S-plane means that our feedback is positive, and if the feedback is positive, everything is going to be destroyed. We need the feedback to be negative. So we are going to reshape the transient response with compensators in chapter number 9. Then we do have the chapter 10, because obviously not only root locus is going to be enough for ourselves. We have to move to another one, or we need another response that we call as a frequency. So in frequency response analysis, we are working assessing stability margins via the Bode plot. So what was the Bode plot? It was just a plot that we have the frequency on x-axis for both of them, and we had the phase margin and we had the gain margin, or we have to draw the phase and gain based on the frequency itself, not based on the time. So we are going to consider that to see that what do we have about the angle one and about the gain one based on the frequency. And finally, we have to design it. So it means that we know the condition that our system is right now at the current situation. Then we have to do some kind of designing. We have to shape the bandwidth in order and some kind of steady state error to reach to the thing that we would like. So let's start this conversation with an example. We do have an anchor, the antenna azimuth positioning. Imagine that you do have an antenna, and this antenna should receive all of the signals that you get from this space or from whatever satellite is there into a specific kind of angle. So what you do have the whole antenna itself. Obviously, you do have some movement sections because you have to move the antenna. So you have the position sensor, you do have the rotating section, you do have the motor drive, and you do have the angle itself. So to build intuition, we apply all 4 quadrants to a single system. So our single system, which call it as a plant model, it has this transfer function. So your transfer function means the output divided by input based on the Laplace. So in Laplace 1, we do have the GS is equals to K times S plus 2.43 divided by F3 times S plus 10. As I told you, the very first step for the root locus analysis is that we have to find the zeros and we have to find our poles. So 0 is obviously is negative 2.43, and we do have 3 zeros. At 0, so we do have 3 poles. So we do have at 0, at negative 3, and we do have it at negative 10. So this is going to be the system based on physical constraint, and we do have the K is means gain, and based on changing the K, we obviously change the position of our system based on the zeros and poles themselves. So this is the condition, this mapping the boundaries, root locus analysis. As I just told you, we do have our 0, which is going to be on this guy, which is the circle, and we do have x, or we do have the poles itself. So based on the changes, or based on some kind of the movement of k, that at one point we do have it as 5, then we do have it 10, till we do have the infinite, we can see that what is actually happening to those poles. So as you can see, one pole is getting absorbed by the 0 itself, and another poles are moving toward each other, and then one of them is going to this side, another one going to go this side. So why we're doing that? What is the reason that using the root locus analysis? Because as you can see, is just a very visualizing section of our normals, poles, and zeros itself. The reason is simple. We don't want complex calculation. So by reading this map, the map that we just draw, and based on increasing decay, obviously the positions of poles will change, because poles are the DNA of the system. 0 is just there by itself, by poles are DNA, and they will move based on k. So we instantly find critical gain values and predict the transient responses. So we will talk about it, by the way. We do have overshoot, we do have the settling time, without solving any complex sum-up differential equation. So that's the reason we use root locus analysis. Another thing that we have to see is about reshaping the reality, because so far we saw that the positions of poles and some kind of the zeros is something constant. Yes, if we change the k, we would definitely see some kind of movements in them. Well, what would happen if the movement, or the one that we do have, I'm talking about this movement, as you can see is using this black arrow. What would happen if this movement is not the thing that we like? What would happen if these movements are moving but through the right side of the S-plane? Because we know right side of the S-plane is our limitation. We cannot go there. If we go there, for sure, our system is going to collapse because the feedback is positive. We don't like it. So at this point, we have to do something. It means that we have to reshape it. By reshaping it, it means that we can, by adding some lead and lag compensators, we can move this movement, or we can some kind of move the curve that we had like this to the left side. By moving it to the left side, we're sure that by increasing the k, which is our gain, our system is not going to collapse. So this is about the design rule. Zeros acts as gravity wells. As I told you, poles are DNAs. Poles are the thing that is going to be in characteristic of your system, while zeros are some kind of constant values are there, but they can act as the gravity. It means that it's putting their locus, or the root locus, towards themselves. So by port exert pressure pushing the locus away. It means that obviously we can have some kind of zeros. The zeros is well going to act as gravity point, and it will some kind of pull this root locus, which is going to be our visualization part, to themselves, while we do have the which poles are going to repel them. So these are the two important things about poles and zeros. We will talk about it in detail. Don't worry, I just want to show you what is happening. So as I just mentioned, we do have the lead and compensators. So about the lead compensators, the goal is speed up the transient response. What does that mean? It means that if I can succeed to move my root locus to the left side, I can increase the speed of the whole system. So the transient response would be faster. So how I can do that? By adding the phase pulls the locus left into the stable region. It means that by adding some kind of zeros on the left side, I can guarantee that root locus would move over here. Not only is going to be stable, but it's also going to increase the speed. On another side, we do have lag. Lag is going to fix the steady state accuracy, while lead is fixing the transient one. The lag is going to fix the state accuracy. So the action, it means that alters low frequency gain without destroying the existing transient shapes. So obviously we need that. It means that we need to add some kind of poles itself. On another hand, if you combine your first and second, or lead and lag, you can meet the multiple speeds simultaneously and synchronize the main manipulation. So we will talk about all of them in detail. Another important thing is about crossing the domain boundaries. It means that so far, or most of the time, we talked about the time domain, or we talked about the S-plane. So in the time time domain, if you consider that time is your main constant or is some kind of your main variable based on the changing of the time, you do have some changes in what? It means that for each control system, you would specifically have the value, or you have your desired value. While on another hand, your actual value or your output is not necessarily going to be as the same as your desired variable as the very beginning. By changing the time, the output variable would be changed. So this change could be like this. And as you can see over here, we do have the concept name as overshoot. It means that the maximum distance between our actual value and the desired value. On another hand, we do have the settling time. It means that the amount of time that it takes for our system in order to reach to the point that we call it as the error of 2%. Somehow at the settling point, which call it as a settling time, the error, we know that error is difference between the actual value subtracting by the desired one. So this is going to be your error. So then what is the error exactly itself? It's going to be the difference between the actual value and desired one. This is something that we call it as the error or steady state error. So far we talked about the time itself. But if you would like to talk about the other aspect, if you would like to talk about the frequency, we need another concept that we call it as a Bode plot. So root locus was focusing on the time, and it's perfect for the initial reaction, while the frequency response is going to be for the long-term stability against varying input. By varying input means that varying frequencies that we have, and we can do some kind of consideration and do some kind of research related to the phase and related to the gain itself. That's why we do have that. So the anatomy would be like this. We do have the frequency analysis. It means that we do have a frequency on the x-axis. As you can see over here, frequency is not start from 0 to some kind of 1000, right? If we would like to do that, it means that we have to scale up the x-axis. That's why we start from 10, then we do have 10 to the power 1, 10 to the power 0. By the way, it's going to be on another side, or this plus side, it actually should be 10 to the power negative 1. So we do have 10 to the power negative 2, 10 to the power negative 1, we do have 10 to the power 0, 10 to the power 1, 10 to the power 2, until 4. So by having different kind of frequencies, we would like to do some kind of consideration that what would happen to the output gain and what would happen to the output phase. Because as we know, in the real world, it doesn't necessarily mean that whatever change that I'm doing in input and everything gets inside the box is going to be as the same as in the output. We do have gain and we do have some delays. So by gain means that how much stronger the output is while you compare it with the input itself. So we are not going to use the normal gain, because normal gains could be very high, something around 1000, 10,000. As you can see over here, we have to scale it up so high or so much. That's why we are using another factor, 20 log of gain itself. So by using that, we can do a little bit of research at what is happening over here based on the gain. On another side, we do phase delay itself, and we can see what would happen with different frequencies. Another important strategy or another important use case of these guys would be about the frequency. It would be about the filters, and we can see that the high pass filter or low pass filter, what would happen to them. Another thing that we have to consider by using the Bode plot is about stability margin, because as I told you, K can be high, can be low, but we still need to know some kind of values for them, because if we increase or decrease it too much, it means that our system is going to be unstable, which we don't like it. That's why we need the stability region or stability margin. It means that how much I can increase the gain by knowing what? By knowing two things, phase margin and by doing the gain margin. So by knowing these two, it means that I can understand how much I can increase the gain while I make sure that everything or every system is going to be stable. We will talk about it. Then we do have the shaping the curve. Obviously, as I just mentioned, we do have one part which is going to be study, which we are going to see that what is happening with the current situation, and then we can do the designing. So by designing means that, again, still we do have the frequency and we do have the magnitude or we do have the gain, and we can see that what would happen if we just increase the K, what would happen to bandwidth, what would happen to the whole scenario. And not only we can do that, we can again put some compensators to make sure that everything is going to be steady staple, which is going to be our final chapter. So again, about the compensator matrix, which is very important part in root locus action and in some kind of Bode plot. As I mentioned, we do have the lead compensators. It is going to improve the transient state by adding what? By adding phase or by adding poles. By adding poles means that our pool, some kind of root locus is going to be pulled onto the left. What would happen to Bode plots is going to increase the phase margin and bandwidth itself. Then we do have the lag compensators. The lag compensator is there for improving the steady state error by doing what? By adding packs of poles and zeros in the near origin itself, which is going to be over here. Why we are trying to do that? Because we would like to some kind of move it a little bit onto the right. So this guy, what is its impact on the Bode plot is attenuating the high frequency gains itself. On another hand, and on maybe the final part, we do have lead and lag. So what would happen if I would like to have both of them at the same time? So I would lose their complex locus reshaping. And obviously I can combine the low and frequency boost with high frequency, and we do have some kind of phase lead over here by using lead and lag itself. So I do have two very simple examples that, again, what are the strengths and what are the weaknesses about the root locus and frequency response. As I just mentioned about the root locus method, the strength is that extremely intuitive for visualizing designing transient response about the damping and settling time, which we just saw it. But what are the weaknesses? This guy is relies heavily on positioning a flawless mathematical model of the physical plant. It means that you have to find roots, you have to find the poles by increasing the number of gain. You have to do all of those mathematical things. Yes, I told you that we don't have to do a complex ones, but still we need to do that. Yes, so if we do that one, we still have to make sure that whatever value that we put there is going to be completely right, because we would like to visualize everything. On another hand, we do have the frequency response. We do have both methods. What is the strength? This is highly robust and can easily handle on-model dynamics and measure the real-world data directly. That is a good one. The weakness, the transient are informed indirectly by a bandwidth rather than the some kind of seen explicitly on the map itself. So it is highly related on the bandwidth itself, which don't worry, we will cover both of them soon. So here's the final part. Here's the final chapter, final slide of the first chapter, that is about the control designer workflow. It means that first of all, we are going to sketch everything by hand based on the transfer function, based on the poles, based on the zeros. We would sketch it on the paper so we understand the structural limits before touching the software. Then we do have some kind of the physical interaction. We do have the physical section. So we have to implement whatever that we had or whatever that this guy had. We have to do some kind of study over them. So we have to see that our values or whatever that we did is going to be right or not. By getting some feedback, by getting some understanding, we can have validation of computationally. It means that at this point we are going to use the simulations to verify the specification, and iteration. It means that we do have the sketch part, we do have the physical part or actual on, and we do have the simulation part. So at this point, we would like to talk about the architecture of the control system. And this is from the very beginning to the end. So from everyday intuition to engineering reality. So let me start with a very simple example. When we are talking about the controller, most of the time we are talking about machines, we are talking about the sensors, we are talking about a very huge or maybe a small physical or some kind of practical thing we do have in the life itself. But let's talk about it about under our skin. So because we know the temperature of our body should be maintained at around 37 degrees, right? So it means that our body should maintain everything around itself in order to make sure that our temperature of our body or under skin is going to be 37 degrees all the time. So what we do have, the plant is going to be the body itself. We do have the muscles, we have the organs, we do have the blood vessels. Then we do have the controller. The controller should check the target or the difference of the target and the actual value of the temperature itself. And by giving some kind of commands to brain, to the nerve system, and to the hormones, make sure that it can some kind of control it. Why is it a controller? The controller is our actuator. It means that by sweating, by shivering, or by whatever that we have to do inside our body, we make sure that our body temperature is going to be controlled, or is going to be 37 degrees. So that is a very important part. So let's talk about these steps again one by one. At the very beginning, we do have the reference. Again, this example could be used for any control system that you have. It could be for body, it could be temperature of the room, it's going to be the speed for the cruise controller, it could be for anything. So we do have the reference. The reference shows that what is our target value. Then we do have this small guy. What is this small guy? This small guy is going to find the difference between the actual value and the reference itself. And by giving it some signal or commands to our controllers, is going to say that the controller should act based on whatever actuator it has in order to do some kind of changes in our actual output itself. So we do have the reference, we do have some kind of feedback that we get it from the sensors itself. Then these guys are getting inside the controller, and by controller, by having different kind of actuator, it would give some commands to our plant or to the system itself. So plant will receive those responses and then would react. So based on react, we do have the actual output. Again, this actual output is going moving through the sensors, so we do have this reference, and everything is going to be iterated till it will reach to the error or the steady state value that we would like. So let's see a very small difference between the open loop and closed loop architecture, because so far we talked about the closed loop. But what was the open loop? Open loop means that you do have, for example, when you go to the shower and when you some kind of increase or decrease the valve in order to reach to the hot water, to the temperature that you want, it's just an open loop, right? Because controller sends the command without sensing in an output. So yes, if you connect yourself to the system, you would be closed loop. But imagine that valve is just by itself. So that is completely open loop because it doesn't have any sense from the output side. But if you connect yourself, you're actually sensing. So by sensing the output and by comparing to your target value, which means that it's suitable for your skin, you're actually adjusting it. So then we do have the analogy. So you put the 6 at fixed position. If water pressure drops elsewhere, you get the cold water. It means that it doesn't matter if something happened to the other side of the system, because we know in controllers, our device or whatever we have is not going to be just based on itself. At some point, it could have some impact from other side. It's something we call as disturbance. So if any disturbance happened to your system, is not smart enough to adjust itself. Why? Because it doesn't have any feedback. It doesn't know what is happening. It assumes that whatever value that I set is going to reach to the thing that user wants. That's why it just have this fixed value. You can't do anything. On another hand, we do have this guy, which means that it's going to sense the outsiders, and it's going to see whatever happening based on the disturbance, based on the actual output, and it's going to adjust itself. So we do have obviously some kind of advantages about open loop, right? They are simple, they're cheap, we don't need to any sensor needs this, so we don't have any complexity. On another hand, but we do have this guy as a closed loop. While it is complicated and it's a little bit expensive, we do have the controlling disturbance by using some kind of the actuator, and we can have the robust change in our plant system itself. And obviously we do have disadvantages because this guy is completely blind, but on the other hand, the closed loop system is complex, is some kind of expensive. It completely related to your work that which one of those systems you have to use. It doesn't necessarily mean that open loop is bad or closed loop is good. You have to check the condition. Let me give you another example. The feedback shrinks errors and reject disturbances. What does that mean? Imagine that you do have your car and your car is some kind of on the mode by itself. It means that you push the pedal and it's just moving with its speed. And your target speed is this guy. But remember, you don't have any closed loop system. You don't have any feedback. It means that whatever disturbance or whatever hill, whatever bump is happening to the system, it's going to reduce the energy or is going to reduce the speed. And that speed is going to reach to that level. If you don't push any pedal, if you don't have any cruise control system, that speed is going to stay constant all the time. After reaching to one disturbance, it just collapses. But what would happen if you do have the closed loop? If you do have the closed loop, that guy is going to check the error, which is the difference between target and actual values all the time. by the way, your cruise control. So the cruise control is going to see that, it's going to have the hill, and then the speed is going to reduce to say that what is happening then. After that, your disturbance, some kind of rejection would get activated. It means that at this point, your cruise control system knows that it has to inject some kind of power, it has to push the pedal in order to reach to the speed that it likes. Why? Because it just designed to reach to the error of 2%. So that's a good thing about the closed loop while it's in comparison with the open loop. So we do have the error reduction. It means that whatever error that you had over here is going to get smaller and smaller. Then we do have the disturbance rejection. The disturbance means that this hill and it's going to some kind of reject this value. And finally, we are going to improve our accuracy itself by closed loop. So as I just mentioned, so far we talked about the physical responses. It means that whatever happened to output, you some kind of compare them together to see that what is going on. So in order to see that, or in order to calculate, or in order to compute that, we need a function that we call it as a transfer function. So transfer function is some kind of output divided by input itself. So output could be anything, or it could be, for example, is the temperature, while the input is going to be your input power. So by reading this part, this guy is going to describe that how strongly a system responds to the input itself in the frequency domain. Remember, we had the time domain, but time domain means that you have to deal with so many complicated scenarios. You have to talk about the derivatives, integrators, and then you have to combine them. So it would be so harsh. That's why we have to work in the frequency domain. And in the frequency domain, but we do have the Laplace, some kind of equations that I will talk about it. So far, we can have an example over here. For example, the heater example. Imagine this guy is the transfer function. The output divided by input is K divided by tau S plus 1. So K is the gain, which is something that we would see a lot in the future because we have to change it. The tau is the time constant. What was the time constant? Probably you saw that in the capacitors and inductor in charging and discharging, means that how much does it take for your specific component or for a specific system to reach to the 63% of its final value. So the exponential rise in room temperature dictates how slowly the room responds to the heater itself. It means that input and output are completely related to each other. So the closed loop equation, so the engine of stability is actually going to be something like this. We know about the GS. The GS means that whatever equation that we had related to our transfer function. But as I just told you, we don't only like that. We just don't want to see that whatever happened to output based on the input. We would like to control it, right? That's why we do have the CS. It means that the CS is going to be your controller. So what was the controller? The controller was about lead and lag and maybe the combination of those. Why we do have that? Because when we change the gain or gain it over here, we do have some changes. We do have some changes in our system itself. But at the same time, we would like those changes to act as favor of ours. We would like them to act like the thing that we want. That's why we need the controllers. We need the CS. So CS guy is going to inject some kind of changes to the system and we make sure everything is okay. Not only that, we have to make sure that we do have a feedback. So that feedback is going to show itself over here in the denominator. So where the TS is the new transfer function based on the feedback. So the GS is going to be your main or is going to be your plant. The CS is a controller and we do have this. So why does this matter, by the way? Because this denominator determines if the system stays bounded, how it fast settles, and how close to the target it gets. So this is important that we have to read this one. We have to understand this one. So what is our job? Our job is to choose the right CS to reshape the denominator to meet our specifications, because denominator, which is the home of poles, is very important that we will talk about it so much. So again, why we need the precise design? Imagine that we don't have it. We don't have any aircraft that can fly stable. We do have the power grid that suffer from the blackouts. We do have a robots damage themselves. We do have the car engines and so on and so forth. So why need this design? Why we do need this CS? Because we have to make sure that we do have the stability. We have to make sure that we do have enough speed. We have to make sure that we do have the minimized overshoot. We do have to reject the disturbances, we have to achieve accuracy, and finally we have to minimize the amount of energy that we use. That's why we need all of these, not against complicated, but in details, some kind of control design aspects of our system to make sure that we reach to all of them. So let's back to our antenna. So our running case study, our antenna, which we are going to see that a lot, by the way, till from the beginning to the end, we are going to mostly focus on this specific example. So what we had the input of sine wave that they're going to point out in 45 degrees. Then we do have the sensors. The sensors and actuator are based on what? Based on some kind of accurate or how good those input is. The output is going to be compared with this input, and we would like to increase the gain. It's not just about the gain. We have to talk about the phase delay. That's why when we are talking about gain and phase, we have to work on the Bode plot. So root locus is just about the system itself, while Bode plot is going to read what would happen with different frequencies. So this GS, which is going to normal transfer function, is not just normal without any compensator, mathematical model of output divided by input. You can see that we do have 1, 0, and we do have 3 poles. So poles are the DNA of your system, while zeros mostly they're going to as the gravity part. By increasing the gain or by decreasing the gain, we can see that what would happen to our system itself. So finally, why we are designing that? Because as I just told you, we would like to reach to the zero steady state error. Zero steady state error means that after maybe 5 tau or after whatever high number of t or the timing, we have to reach to the error of around 0. It means that the difference between our target and between the actual value should be something around 0. Then we are talking about the settling time. It means that the mechanical movement, it must be swift and settle completely within the 5 seconds. So imagine that our settling time, the timing that we would like to have for our system to reach to the gain or reach to the some kind of value that we would like, is 5 seconds. Why 5 seconds? Obviously, we cannot move fast, because when we are talking about the antenna, this actuator should have enough time to move this heavy thing to the left or right or whatever maybe rotation that it has. Then we have to maximize the overshoot. So we need to some kind of we need to work on the maximum overshoot. Obviously, not maximize that, because we don't want this overshoot to be so max. We don't want our some antenna or the speed of the car to increase and decrease. We will like to have the reasonable value for our maximum overshoot. And finally, we don't want to have some kind of disturbances. It means that it's completely inevitable. You're going to have it, but you have to get rid of that. How? By using some kind of disturbance rejection. It means that anything that would happen because of the wind, because of whatever, for example, the foggy weather or whatever that you have to make sure that you're going to reject it completely. And in order to do all of that, to some kind of do the root locus, do some kind of Bode plot, we need a couple of things. Obviously, the first part is about finding the place of the poles and zeros by knowing the fact of the difference between real numbers and imaginary, which is obviously so easy. Then we have to calculate the differential equations, which means that derivative and integrative. Probably we are not going to touch it that much, but we have to know the concept. Why? Because we have to convert these two guys to the frequency responses, to their Laplacian equations. And obviously, we have to know some kind of linear algebra related to the eigenvalues, related to the poles itself. And finally, we have to know the first and second order differential equation. We will talk about all of them. So obviously, you need a paper and pencil, you need that MATLAB, and we do have all the software that we need. That's why our chapters are going to be meaningful right now. The chapter number 8 is about the root locus analysis. The chapter number 9 about the root locus design. The chapter number 10 is about frequency responses. And finally, we do have the frequency design. So let's talk a little bit more in detail and actually why control systems matter. We talked about it so far, but let's see it with actual examples. There's a video, actually this is just a PDF, so I couldn't put it over here, but there's a video about the Tacoma Bridge collapse. I do recommend you guys to go there and check what has happened in that video. It's just about 1 minute. It's just black and white because it's back to 40s. What was the idea? The idea was building a bridge that cost around $6 million to connect two places together. What happened? After a little bit of wind, or after a little bit of an incident that because of the weather obviously itself, the bridge starts to swing. So maybe you would just ask yourself that, okay, normal wind, and actually it was normal wind. It was something around 35 to 40 miles per hour. So it wasn't that kind of a big deal. But something happened to that bridge that actually increased the intensity of the power of the wind itself. what happened? When the wind was some kind of moving from, for example, left to right, or obviously the wind is not going to be in 90 degrees or 180 degrees. Obviously, the wind is going to move like that. It's going to move like this. When wind moves like that, it puts some kind of pressure, it puts some kind of energy to the bridge itself. So maybe you would ask yourself that, okay, the bridge is heavy enough. They do have the cables. We are talking about the $6 million. What happened to the bridge? Actually, it moved because the engineers on that time, they didn't consider the fact that at some point the energy can be intensified. The energy of the wind can be intensified. It means that if you do have enough energy of the wind that's going to be integrated one at a time or by each other, you can have a small amount of swing. So a small amount of swing is not a big deal, but the way that the bridge or aerodynamic parts of the bridge that handles that was the issue. Because after each wind was hitting the bridge, the aerodynamic part should reject all of those disturbances because the wind is disturbances. But something happened, and because of the bad designing in the control section, which we are talking about the aerodynamic, it's about physical part, we don't know anything about it, this energy was getting big, it was getting more and more and more and more till the fact that your bridge is going to swing to the left. So obviously when bridge swing to the left, your wind is not going to move from just one side to another one, right? We also do have some wind from another side. So the direction, the power of the wind would change. That swinging in some kind of bridge was moving like this. As you can see, the bridge was, rather than just getting rid of or reject that disturbance, it was increasing that intensity. It means that the wind was pushing and bridge, rather than just fixing that issue, was increasing that. Imagine that if you would like to imagine that in the closed loop condition, you do have the controller, that your controller, rather than just having the negative feedback, has a positive feedback. It means that the error, rather than just being subtracted by the increasing by the reference. So what happens? The swing from left and to right was increasing and increasing, and at some point bridge collapses. So it means that $6 million is gone, your bridge is gone, all of the efforts is gone. Why? Because you didn't consider the fact in aerodynamic. What was that? The system failure, the aerodynamic resonance matched to the natural frequency. So what is this? What's the natural frequency? Natural frequency is something maybe you know as omega n, is the amount of frequency that your physical thing. For example, the swing, it could be whatever or for example, whatever that you have. They would like to work on that specific frequency. So if you do have a wind, and wind is going to act as a periodic wave, and the frequency of that periodic wave or periodic move would be as the same natural frequency of your bridge or whatever controller system that you have, you reach to the collapsing point. It means that those frequencies are going to match each other, and the poor damping created positive feedback. It means that rather than just getting rid of those some kind of issues or disturbances, you are going to have positive feedback. This positive feedback was increasing and increasing, and after that your bridge collapsed. So results, the total collapse in just 4 months, millions in economic loss. So what did they learn? They learned that in order to correct that issue, they have to have addition of tuned mass dampers. It means that they have to consider some compensators, which we are going to talk about it, in order to get rid of this rejection. Because when you build something, you don't have that. If you just follow all of those mathematical rules, all of those physical rules, all of those aerodynamic rules, you still have some issues. But you have to consider some compensators. These compensators could be cables, could be the way that you structured your bridge. You have to consider that in order to make sure any kind of disturbances, like wind, like could be the high load of cars over the bridge, is not going to cause any kind of issue. Or at least if this causes an issue, it's not going to reach to an end, to collapse. So the system success, what happened? They improved aerodynamic designs artificially by increasing the damping. And finally, the result, the zero collapse, structural stability maintained. So what we learned from this incident, that you must understand the response, the resonance and damping. The damping means that how much some kind of resilient your system is against all of the disturbances to reach to the steady states that we like, or via seemingly small forces will cause the catastrophic failure like the way that it did. So it means that we need to have a trade-off, the trade-off triangle. The trade-off triangle will tell you that what do you need and what you should do. At some point you need the speed, you need the fast response, and at some point you need robustness, stability against uncertainty, and at some point you need the accuracy. But not all the time you need one of them or you need three of them at the same time. Imagine that you do have the sports car luxury sedan. So for this one, we do have the stiff suspension, we do have the bumps felt with soft suspension. It means that between the sport car and luxury sedan, because in a sports car obviously you need to be fast, you need to be some kind of you're in the race and you're in the competition, and whatever is happening, whatever turning, whatever curve that you have, you need to be fast. You're not to be some kind of comfortable. That's not the luxury car, so it needs to be fast. So it means that you gain something, you lose something. On another hand, in the luxury design, for example, you're in the limousine, so when you're inside of that and when you hit any bump, you barely feel anything. But if you have that hit in the sports car, you feel everything. That's why it's so stiff. On another hand, luxury car is not designed to act so fast. If you reach to some kind of turn and some kind of curve, you cannot immediately turn your wheel and expect that your car is going to move. No, it takes some time, because the design inside your luxury car is very, very different from your sports car. So at each point, you have to see, you have to know, you have to understand your system. Then based on that, you have to consider some factors like some kind of designing, some kind of way in order to change the condition inside of that to make sure you reach to the thing that you like. So translating the physical reality into the predictive math. So this is actually we are going to do. This is actually we are going to consider, because as I told you, we do have our physical system, we do have the input, and physical system for us right now is going to act as a black box, and we do have the system is going to be mathematically studied. So what is happening at this point? If we do have the control engineering workflow, your workflow should be like this. The stage number one, the physical reality. There could be that bridge, it could be some kind of the normal RC circuit, could be anything. Then you have to consider the time domain calculation, which we know as calculus. Those derivative, integrative, those whatever combination of them, that could be your time domain calculus. Then we do have the frequency domain. It means that we do have the Laplace equation. You move from the time domain to frequency domain, and finally we do have the algebraic blueprint. When you have that, you can talk about the GS, you can talk about the input, you can talk about the output, you can talk about the gain, you can talk about the compensator, and you can talk about anything. So what do we have about the physical laws? Imagine that we do have just a simple RC circuit. As you know, based on KVL, the voltage of your source should be as the same as the voltage drop over the resistor and the capacitor itself. So Vn is going to be RC times dVc divided by dt. By the way, C dVc divided by dt is the current that passed through your capacitor plus the voltage of capacitor itself. So this is the first order system. Why we call that first order? Because the only derivative part that you have is related to capacitor. That's we call it as first order system. On another hand, we do have the mass spring damper. So what is the formula over here? Then the some kind of F or the Newton is going to be equal or is going to be related to the mass, and it's going to be related to other factors. But as you can see, we do have the derivatives to the power 2 of distance, and we do have the derivative of power 1 of distance, and we do have the distance itself. That's really as what? As the second order system. So the highest derivation, the highest derivative dictates the system orders. It means that I do have the number 2, I do have the number 2 of derivatives. This is going to be a second order system. The system orders and determine its fundamental capacity for oscillation and energy storage. So let's talk about the fun part. The fun part is that we would like to escape the time domain. Why we would like to escape that? Because considering all of those integrative derivatives is going to be so harsh. And right now we are talking about normal system. Imagine that your system is going to be so much complicated. How you can handle all of those by considering any kind of condition, it would be hard. So it means that at one point we do have the continuous physical system, we do have the complex calculus, we do have a differential equation. We don't like them. That's why we use what? The Laplace Laplace transformation. It means that this guy is going to get the input and move it to the frequency response. So at this point, we do have the complex frequency, we do have the some kind of simple algebra and the ratio of polynomials. So the Laplace transformation is going to project, or is going to move whatever calculation that we do have from the function which were the continuous of the time into a complex frequency space. And calculus, because algebra, we like the algebra, so let's talk about it. So let's talk about this kind of a dictionary. I mean, it is rare that you would touch that part, because most of the time we assume that we are already in the Laplace equations or we are in the frequency response, but that is good to know that. So imagine that you do have some impulse. This impulse is the small delta t. It means that this kind of the happening, so the output in the Laplace would be 1. If you do have a step 1, it's the step t is going to be 1 over s. You do have the exponential e to the power negative alpha t is going to be 1 over s plus a, and you do have the oscillation, it would be omega divided by s to the power 2 plus omega to the power 2. So we transfer from the complex or from the calculus to algebra itself. So it is very important that so far we saw the transfer function, but we talked a little bit about the poles and we talked about the zeros, but we didn't actually touch that. What is happening actually inside of it? What does those power means? What does the some kind of those s means? And what is happening exactly there? As I told you, when we were talking about the transfer function, we talked about two important parts, zeros and poles. What are zeros? Zeros are the roots of your denominator. Whatever that you have, there are going to be your zeros. What are the poles? The roots of your denominator. But there are two more important things. As you can see, obviously, I don't have s to the power 0 or s to the power 1 all the time. I do have s to the power 3, s to the power 4, s to the power 5, or whatever number that you have in your side. The biggest number, or the biggest number that we do, biggest power that we do have, for instance, at zeros, is going to be the degree of our zeros, or degree of the denominator itself. So these determine the relative magnitudes of response components together. Why we would like to know the degree? Because at the end of this slide, I will tell you that how you can compare those and how you can intuitively decide that your system is going to be stable or not. So far, understand m is the degree of your denominator, or the degree of your zero. On another hand, we do have the degree of denominator, which is going to be the degree of your poles itself. Why we care about that? Because there's a rule, the constant rule, that says that in the real physical system, if the degree of your poles is bigger than your zeros, or number of poles is bigger than number of zeros, means that we do have something like this, everything is okay. Everything is some kind of, at least at some point, of stable. Otherwise, high frequencies would amplify the intensity, would amplify this kind of the system itself and violating the physical laws. The one thing that we saw in that bridge itself. So that was one of the issues that happened, because the high frequency, the wind had some kind of the higher frequency. By the way, when you're talking about the high frequency, we're talking about something like this sine wave. The lower frequency would be like that. You know about it. So that high frequency was intensified, and the output of getting more and more and more, so everything is going to collapse because the output energy is going to collapse. So you're going to use the S-plane. What is S-plane? S-plane consists of two things. If you remember about some kind of normal coordinate plane that you have X and Y, at this point you do have two axes, as the real axis and imaginary axis. Obviously your poles or your zeros are not going to be some kind of real numbers all the time. Some imaginary. So you have to show them. We do have the different kind of quadrants. As you remember, we do have 1, 2, 3, and 4. But when we are talking about the frequency responses, or when we are talking about the real and imaginary part, we just care about two segments, two sectors, the right side and the left side, while the real part is positive, while the real part is negative. If you're moving through that part, we do have two conditions. We do have the marginal stable, and we do have unstable condition. So obviously you can tell that at these 2 points, we don't like it that much. They're still going to be at or this kind of and at another point is going to be completely on the right side. Because again, poles are the DNA of the system. One thing that we care most is about the poles. We use zeros most of the time as a way for the compensation. Imagine that your pole is completely on the right side, system is unstable. After some point, your output is going to get more and more, and feedback is going to be positive rather than be negative. If you have your poles at this point, your margin is stable. But on another hand, if your poles are going to be on the left side, we do have the stable and we do have another stable situation. That's why we like the right more, and we hate right and we like left. So again, the zeros, as I just mentioned, they're going to control the transition path. They're not that kind of important or some kind of final values, because as I mentioned, the poles are going to decide, or they are the DNA of the steady state variable, while this some kind of zeros are the transient path. So the zeros are, for example, at s is equals to a, because if you would like to find that, you have to simply make it at 0, is going to be the right half plane. So zeros do not cause instability, but they drastically alter the response magnitude. Imagine something like this, that you do have your time, and after that you do have your some kind of the output response. At the first point is going to decrease, then is going to increase. So at the steady state, if we assume that because all of the poles that we do have are on the left side, so everything is going to be stable, but the matter of how it can be stable, it's related to the zero itself, that we are going to talk about it a lot. So most of the time we do have this kind of forms. The very first one is about the time constant form. What is that? It means that your transfer function is like the k divided by ts plus 1. We saw it in the thermostat part. So this is, guy, the the superpower is that we can just use it in the hand analysis. So inside is going to immediately reveal that physical time constant t and dc gain. Dc gain means that your s, which was in the frequency, is going to be 0. So you can immediately find your dc value or your dc gain. Another thing, you can find the time constants. That's why we loved it. We do have this guy, and we can find the time constant, and we can find the gain itself. On another hand, we do have the polar zero form, and it's going to be something like this, that you are going to see it a lot. The k, which is going to be gain, the time. On the top side, you do have the s plus z. Obviously, you don't have only one, you have the multiple of that, but all of them are going to be multiplied. On another hand, you do have the same thing on the some kind of denominator, which we're going to consider as the pole part. So the inside, the original setup for root locus and Nyquist design plotting. So what is Nyquist plotting? This guy is going to be used for the designing of your PID controller, that probably we are going to touch it on the chapter 11, which is chapter 11 of your work. So then we do have the standard second order form, that we do have it like this. If you remember, that was the time when you have the sine wave as your input. So you do have this guy. So this is going to be the transient prediction, and we are going to see it, which are working with natural frequency, and we are going to work with damping ratio. So most of the time, we are going to work with these two guys in order to actually study the system, our system, to make sure that everything is fine. If it's not fine, use some kind of compensators itself. So the anatomy of the second order system, as you guys remember, we were talking about this right now we are talking about this guy. This is the second order system, and it has two important factors. It has the omega n, which is natural frequency, and which we do have it, this guy. You can call it as some kind of the zeta, actually is the name of that. It's a little bit hard to some kind of draw, but this guy is the zeta. And zeta will tell you a very important story. If your zeta is going to be smaller than 0, it means that your system is unstable. It means that after some point, your system is going to be bigger and bigger. And your zeta is between 0 and 1. It means that your initial condition would be high, while the steady state point is going to be low. If your zeta is going to be 1, it means that you have the critical damping. What is critical damping? Critical damping means that you don't have any oscillation before reaching to your steady state point, while you have the maximum speed, or you do have the smallest amount of time constant. On another hand, we do have overdamping. Overdamping is somehow like the critical damping, but as you can see, the speed is going to be a little bit higher, and probably you are going to have some steady state error itself. So the system types is about the power of integrators. So we do have some kind of, when we are talking about integrators, obviously we are talking about 1 over s, because if you remember, the integrator of ft dt is going to be something around 1 over s. If you don't consider the fact of initial condition, it's going to be like that. So whatever we do have the type 0, that means that that you don't have any integrator. Whatever your step input comes in, you do have this, whatever some kind of your ramp input, and whatever your parabola input, another type of the inputs itself. We are not going to talk about it so much. Most of the time we do have the step input and we do have the ramp input. The type 1 means that you do have one integrator, and if your input is just like this, your output would be like that, and if your input is like this, your output would be like that, and it's just about the parabola one. The type number 2 means that actually 1 over s to the power 2. So if your input is like this, the output is like that, and if your some kind of input is like this, your output is going to be something like that, so on and so forth. It's not very important to know this part right now. I'm just going to give you a very heads up that what does it mean by 1 over s, 1 to the power 2. Actually, that means that integrators, or maybe integrators to the power 2. So every pole placed at the origin s is equal to 0 acts as an integrator. You are going to see that in the future, that at some point your transfer function is going to have just s in the pole. So what does actually mean? That guy is going to be your integrator. So it's going to upgrade the system ability to perfectly track increasingly complex moving target. Why will integrators? Yes, at some points maybe you would say that, okay, integrators means everything should be add up, because when you're talking about integrators from one point to another, actually you have to find the area, or you have to find the area beneath the line itself. But at some point is going to give you a very, very good, is what is happening from, for example, a specific time at 0 or whatever is that at the beginning to the time that you like. If you guys remember, we talked about the DC gain. So DC gain, just like the normal part that we had, it's about the DC value of your electrical circuit. For example, you have the voltage source, it has the DC value or DC offset, and you have the AC value. So DC gains means that at the very, very beginning of condition, at the very beginning of the as I mentioned, the DC gain is going to give you the response of the system while your input is going to be something constant. While it means that constant, it means that it doesn't have any frequency. Imagine that your GS is whatever is that, but you would like to find the value of G0. It means that what would happen at the end to your GS if your S is going to move to 0? Imagine that you do have your some kind of values, for example, to the voltage, and that one follows a formula 1 divided by 0.001 times S plus 1 itself. So if you consider that S is equals to 0, it means that if you consider that your input is something constant, obviously your output is going to be something constant. That could reach to after some time, but you know, if your is 0, or if your value is constant and it doesn't have any frequency, your output is something constant, and we call this DC gain. So it means that your capacitor is going to get fully charged and holds a fixed steady state voltage. So the antenna motor, we care about that one, but one issue it has is actually, if you remember from the formula, we had S in our poles itself. So S is equal to 0 is going to give you a DC gain of infinite. So due to the pole at S is equals to 0, so this continuous voltage is going to result in endless rotation, not a fixed angle. That's why it's important. That's why we have to fix this issue. So the translation is complete. Right now, we do have what? Right now, we have some kind of physical system mapped by a differential equation. For example, we had our circuit. Then we do have the time domains escaped by a Laplace transformation. We do have the time domain from the calculus. We just moved to algebra, and the future behavior is going to unlock the via poles, zeros, and standard forms that we are going to touch it actually.